Welcome to Spring LIB.
Okay, let's recall how adding chlorine across a double bond works. First, we end up with this, the sort of cyclic intermediate, and that this will happen on one face of the double bond. And then finally, there'll be attack from another chlorine molecule, which will open up that cyclic sort of ring structure. And eventually, we'll get anti-addition of chlorine across the double bond, meaning there'll be one that's coming towards us and one that's going away. And the same thing is true for this cyclohexene, which means that we can really conceptualize a bunch of different ways that this can add. And what we've got to determine is are those any of those bunch of different ways of adding equivalent? So if we consider all the different ways we could add chlorine anti across this double bond, there's really four ways we can do it, right? We can do the top one is a wedge, and the bottom one is a dash. Sorry. We can do the top one is a dash, and the bottom one is a wedge. Oh, wait, that's it. Yeah, because I forgot to add anti, right? So then the question becomes, are these the same product or not? Are these enantiomers or are they the same molecule? A way you could answer that is by determining whether or not this has some sort of internal mirror plane of symmetry, right? Because if it's a diastereomer with a mirror plane of symmetry, then they're just the same molecule after all. But I'll tell you, I mean, I don't know how to prove it quite exactly. I guess one option might be to just determine what the stereochemistry of each of these centers is and then present that, which might not be such a bad option. Like this is going to be the highest priority, then this is the second highest priority, and this is the third, and we've got hydrogen in the back, right? So that makes this upper one R. And for the lower one, we've got the chlorine is the highest priority, the second priority is up there, and the third highest priority is down here with the highest priority hydrogen in the back. So it looks counterclockwise, but since the hydrogen is in the front, even though counterclockwise would suggest S, it's actually R because we don't have the lowest priority substituent in the back. So this is the RR enantiomer, for example. And we could just as easily determine that this must be the SS enantiomer, right? Highest priority, second highest priority, third, hydrogen's in the front. This appears to be clockwise, but since hydrogen is in the front, it appears to be clockwise, which would suggest R. But since hydrogen is in the front, we know it must be S. And for this lower of the two substituents, we could say this is the highest priority, this is the second, this is the third, and it's counterclockwise. And since we have the lowest priority in the back, it is in fact S when the priority direction goes counterclockwise. So this is the SS enantiomer. All right, so we've got the RR and the SS. And RS isn't possible, and neither is SR, right? Because we need these two groups to add anti, because that's how adding Cl2 across double bonds is, right? This is not a possible product given the conditions. You will always get the anti addition.